Well, friends, we will continue our journey looking at confidence intervals, and don't give up on me. We will get this down. The real purpose of doing a confidence interval is not to go in a population and say so many percent of the data lie from point to point. The real purpose is that we do not know the mean of the population, the standard deviation, variance, or the number in the population. The real purpose is to take a sample, take the mean of the sample, the standard deviation of the sample, the variance of the sample, and the number in the sample, and then describe information about the mean of the population. And we can infer things about mu. We don't know the mean of the population, but we can infer that the mean of the population lies within a certain range. Once we can infer the mean of a population lies within a certain range, then we can test an hypothesis or a claim by a manufacturer to see if it appears to be true or false. That's going to be the next section. I'll remind you of these critical z-score values for 99% all the way down to 70%, but I remind you that the ones that are most used are 90%, 95%, 98%, and 99%. Rarely do you do an 85, 80, 75, or 70% confidence interval. Now, here's a very important concept. It says if we take an infinite set of samples of size n, in other words, maybe we want to sample 100 samples out of 100 data out of a population. If an infinite number of samples of size n are taken, the sample means of those infinite number of samples will be normally distributed around mu, with the standard deviation equal to the standard deviation of the sample divided by the square root of the number in the sample. Now, this is a very powerful thing. That says that if we take an infinite number of samples, then all of the x bars of those samples will be normally distributed around mu, and they will be very tightly clustered around mu with a standard deviation equal to s over the square root of n. Now, if x bar is normally distributed around mu, then likely mu is normally distributed around x bar. So, I want you to think about that just a minute. I have myself and my wife. If my wife is normally seen with me, then I am normally seen with my wife. So if x bar is normally distributed around mu, then if we select an x bar, mu should be normally distributed around it, according to the normal distribution curve. The confidence level formula is x bar minus z times s over the square root of n, and x bar plus z times s over the square root of n. I point out to you that this amount z times s over the square root of n is called the effect size of the x bar distribution. Now, to solve for a confidence interval for mu, use the following steps. I want to point out to you that the real purpose of confidence intervals is not to just say data are scattered around mu when we know mu and sigma, because we never know mu and sigma. The real purpose of the confidence interval is that we can take a sample, find a sample mean, and construct a confidence interval around that sample mean in which we have a certain level of confidence that the true mean lies. Now, in order to do these, the first thing you do is you find x bar, s, n, and z confidence. Then you calculate the value of z confidence times s over the square root of n, which is known as the effect size. You calculate the confidence interval. The lower bounds is x bar minus the effect size, and the upper bounds is x bar plus the effect size. I find it easier to work in terms of x bar minus e and x bar plus e, where e equals a value, than to try to stick those into both places. These values provide a confidence level for mu. You are the given percent confidence that mu lies in the confidence interval. For example, you're 98% confident that the population mean lies between 23.4 and 24.1. It's an example. Now, here we're going to do a sample problem. A manufacturer wants to find a 95% confidence interval for an automobile's miles per gallon. A sample of 500 cars has an average of 34 miles per gallon with a standard deviation of 6 miles per gallon. Construct this confidence interval for the true mean miles per gallon. Now, here's a problem that is very much what you may deal with in real life. We don't know what the true mean of the population is, nor do we know the standard deviation of the population. What we can do is we can take a sample of 500 cars, and when we sample those 500 cars, we can determine X bar, we can determine S, we know the number in the sample, and then we can construct a confidence interval for the true mean. So there are things that are interesting here. The sample size is 500, X bar is 34, S is 6. The confidence level is 95%, so we're reading it for information. So we start out, step 1, X bar is 34, S is 6, N equals 500. Step 2, the Z confidence is 95%, which according to our table is 1.96. So we would calculate the effect size. The effect size is 1.96 times S over the square root of N. 1.96 times 6 over the square root of 500. Just put that in an Excel sheet. It comes out to 0.53. So our confidence level is 34 minus 0.53 and 34 plus 0.53, or 33.47 and 34.53. What we know now is that the true miles per gallon of this automobile, based on the sample, we are 95% confident that it lies between 33.47 and 34.53. If you go out and you look at an automobile, and a new one, and you look at the sticker, it'll tell you something about the miles per gallon. It may say it's 34 miles per gallon, but it will give you a range. And that's what they're giving you as a confidence interval. Now let's think one step beyond this. Suppose the manufacturer claims that the real miles per gallon is 38 miles per gallon, and we do a 95% confidence interval, and we find that it's 33.47, in between 33.47 and 34.53. We know that 38 is not in the 95% confidence interval, and we would then reject the manufacturer's claim. This means that based on our sample, we are 95% confident that the true mean miles per gallon is between 33.47 miles per gallon and 34.53. And of course, the more cars you sample, the more narrow the confidence interval becomes, but we've got a fairly narrow confidence interval there. Now, remember that we took a sample and we described the sample. We then inferred the value of mu using a confidence interval. We're 95% confidence that mu lies in this range. Now, I want to point out to you that we can do confidence intervals ad infinitum for just data sets. If mu is this and sigma is that, then here's find a confidence interval. All those is just meaningless exercises. What matters is when we look at a sample and we are able to predict the population mean. That's what really matters. Now, we're about to roar. We're about to go to the next level once we do this. So I just wanted to share with you some of these ideas. You have to continue to climb the ladder, and you can do that one rung at a time. You're making good headway.